Welcome to the physics class. Now it is the second BSc class students, and it is 50 unit quantum theory of radiation. And first of all, this is the Nagabhushanam CH, K.B.N college. In this class, we discuss about the topics like the Kirchhoff's law, Stefan Boltzmann's law, Wien's displacement law, and the Planck's radiation law and its derivation, and the parameters, solar constant, how it is determined, and the temperature of the sun calculation, and briefly these topics will be discussed in this class. And first of all, we start with the black body, the radiation. We know that the heat is a form of energy and it is transmitted from one place to another or from one body to another by basically three ways. They are conduction and convection and radiation. In case of the conduction and convection, there is a need compulsory the medium to transmit the heat energy from one body to the other. But in case of the radiation, there is no need of the medium to transmit the heat energy from one body to the another. So without necessary of the medium, the heat transmission, the process is called the radiation. And the black body means the radiations which are incident on a body, they are completely absorbed when it is cool and when it is at the same time, and it emits also all the radiations of the all wavelengths which are incident on it. That means the black body is defined as it is a body in which the completely absorbs all the radiations of all wavelengths incident on it. So it is a good absorber and also good radiator. Also, it is the black body. And according to Kirchhoff's law, it is the ratio of the for a given wavelength and at a given temperature, the ratio of the mg power to the absorptive power is the same for all bodies, and it is remains constant, and it is equal to the emissivity of the perfectly black body. And the Stefan's law, it is the energy emitted by a black body depends upon its temperature, and as the temperature increases, the energy emitted is also increased by the relation. The energy emitted by the black body per second per unit area is directly proportional to the fourth power of the absolute temperature. And it is also equal to the sigma T power 4, where sigma is the proportionality constant and it is called the Stefan's constant, and its value is the 5.67 into 10 power minus 8 SI units. And the Wien's law, the energy emitted by the black body is directly proportional to the fifth power of the absolute temperature for a given wavelength. And the Wien's displacement law. So as the product of as the temperature increases, the wavelength corresponding to the maximum energy is decreased. That both are inversely related. So the lambda m is the wavelength corresponding to the maximum energy, and T is the absolute temperature of a perfect black body. So its the product is the remains constant, and in it also stated as the wavelength corresponding to the maximum energy is inversely proportional to the absolute temperature, or the product of the wavelength corresponding to the maximum energy and the absolute temperature is constant. This constant is called the Wien's constant, and its value is given by 0.2896 into 10 power minus 2 meter Kelvin. And that means suppose the graph is drawn between the wavelength versus the maximum energy at different temperatures. The wavelength corresponding to maximum energy shifted to a shorter wavelength side. So from this graph we can say that the wavelength corresponding to maximum energy and absolute temperature both are inversely related. And there is the Planck's radiation law. And before we going to the derive the Planck's radiation law, and there are some hypotheses there. Every black body contains a number of molecules. They are in vibrating positions. They are called the simple harmonic oscillators, and they are vibrating with different all possible frequencies. And it is the energy emitted or absorbed is the quantized. That means it is the allowed some particular integral multiples of the some packet of the minimum energy. That packet is called the photon the quanta, and each photon energy is h nu, where h is the Planck's constant and nu is the frequency of radiation, and n is the integer like 0, 1, 2, 3, so on. So here the average energy of each oscillator is given represented by epsilon bar. It is equal to E by N, where capital E is the total energy of all oscillators and N is the total number of oscillators. So by substituting these values E and N, then we get finally the average energy of each oscillator is epsilon bar is equal to h nu by E power h nu by kT minus 1. And the other topic in this unit is the pyrometers. Pyrometer means it is the instrument. It is useful to measure the very high temperatures, and it is working based on the principle of the radiations. Hence, it is also called as the radiation pyrometers. And the main advantage of this instrument is there is no need in contact with the body whose the temperature is to be measured. And the pyrometers are classified into two types. And they are total radiation pyrometer, and other one is the optical or the spectral pyrometers. And one of the optical pyrometer, that is a filament optical pyrometer, and this apparatus is useful to calculate the temperature up to 1500 degrees C, and by using rotating sector we can enhance the temperature also. So briefly, the descriptive this part, the disappearing filament optical pyrometer, it is the telescope, and there are the two parts, objective lens, and other one is the eye side, it is the eyepiece. And in telescope, the crosswires are replaced by the filament, and the distance between the objective lens and the eyepiece is adjusted by arranging the rack and pinion arrangement. And the filament is also heated by arranging a simple electric circuit, and consists of battery, key, and rheostat, ammeter in series connection. And the ammeter useful to give the current strength, the I. And with the help of the rheostat, we can adjust the strength of the current passing through the circuit. So due to this simple electric circuit, we can heat the filament by passing the current. And first of all, the objective lens is facing towards the object whose the temperature is to be calculated, and the rack and pinion is arranged so that the image of the hot body is placed on the filament. Then we observe through eyepiece, and the eyepiece in front there is a red glass filter G, and there are also two diaphragms T1, T2. Both are useful to limit the radiations the enter into the telescope and falls on the filament. And with the help of the rack and pinion, the image of the hot body is incident on the filament. The filament appears brightly, and by passing the current through the filament and adjust the rheostat position, and the current strength is varied so that the filament just disappears. In that situation, the current strength is high, and suppose it is the temperature of the hot body, and where A, B, and C are the three constants, then the temperature of the hot body and the current strength is related by a simple equation I is equal to A plus BT plus CT square. And here A, B, C constants are derived by using three known bodies of the hot bodies, and then we can calculate the temperature of the given hot body. And the other topic in this unit is the solar constant. The solar constant is the solar energy received by the perfect black body in 1 second per unit area, and the distance is equal to the average distance of the sun and the earth in the absence of the earth's atmosphere. And the perfect black body, the surface is incident to the rays normally, and its value is 1340 SI units. And the solar constant is represented by the letter S, and it is determined by the instrument. It is called the angstroms per kilometer. And simply there are the two black body surfaces, so both are identical in all qualities, and they are represented by here in the diagram S1 and S2. And here the S1 is heated by the sun radiations, and they are incident normally. But the second strip S2 is protected from the sun radiations by arranging the double walled shield H. But the strip S2 is heated by passing the current by arranging a simple circuit, rheostat and key and battery. And there are the two instruments, ammeters, voltmeter and ammeter. Voltmeter gives the voltage strength and ammeter gives the current strength. And at the back side of the strips S1 and S2 are connected to the junctions of a thermocouple. And thermocouple, the combination is consisting the galvanometer G also. So S1 is heated by the radiation by coming from the sun, and S2 is heated by passing the current, and both are at two different temperature. The galvanometer shows some deflection, and the rheostatic position is adjusted so that the current strength varied, and the galvanometer shows the zero deflection or null deflection. In that case, both are S1 S2 at the same temperature. That means S1, the strip energy absorbed by the sun, which is equal to the electric energy supplied to the strip S2. So both are at the same condition. Then the solar constant is calculated by using the formula VI into 60 by AA into 4.2, where V the voltmeter reading and I the ammeter reading, and small a the absorption coefficient, and A the area of the strip. So the solar constant is calculated by using this formula, and here the S is the practical observed the solar constant, but actually the true solar constant is denoted by S naught. And here the true solar constant and the practical solar constant S both are related by the equation S is equal to S naught tau power secant Z, where tau is the transmission coefficient and Z is the zenith distance. Here the graph represents the drawn between two parameters, secant Z versus log S. Here secant Z values along the x-axis and log S values along the y-axis. And the graph is a straight line, and it is does not passing through the origin, and it intersects the y-axis. So the y-intercept gives the log S naught. From log S naught value we get the value S naught, where S naught is the true solar constant. And here the temperature of the sun is also calculated by using the solar constant. So first of all, the sun is divided into different layers, and there the central part region, it is a very hot core, and its temperature nearly 20 million degrees. And the boundary of the hot core is the photosphere, and its temperature around 6000 Kelvin. The sun temperature means the temperature of the photosphere. And the next layer is the reversing layer, and all elements in this layer is in the state of the gaseous state. And the next layer is the chromosphere, and it is only appears during the total solar eclipse, and the outer layer is the corona. So here the temperature of the sun is obtained by equating the two energies. One is the Stefan's law, which is equal to 4 pi r square sigma t power 4 sigma 60, where 60 means per 1 minute. And another one is the 4 pi r square into S, where S is the solar constant. And here, by using this formula, T is equal to R by R, S by sigma whole power 1 by 4th, we can calculate the temperature of the sun. Here in this formula, there are some letters are there. They are small r means it is the average distance between sun and the earth, and capital R is the radius of the sun or the photosphere. S is the solar constant, and sigma is the Stefan's constant. So with help of this formula, we can calculate the temperature of the sun. Thank you.